So here we are, fall 2018, question 6A. And the question is, how do you go through a problem like this? And in particular, whenever you're defining a function that you call repeatedly, which seems to be a theme in this course, how do you implement such a function, or how do you think about it? I would say, we're trying to master the skill of building functions and manipulating functions. And a particular variant of that is having a function that you can call multiple times. And that means that each time you call the function, you're going to have to get a function back. Otherwise, it wouldn't work to call it again. And it seems like these functions, you're almost getting back like a variant of the function you had before. So you call repeat1 and you get something. Really get a tablet, shouldn't I? You get like a value here, which is another function. You can tell that because you're calling it. And it behaves kind of in the same way that repeat does, so that when you call it, you get that same behavior. And when you call it, you get that same behavior. So, each time you call it, you're really just kind of doing one thing, but you're getting back as a return value a function that does something similar. And to achieve that is usually involve some kind of self-reference, where basically repeat is going to return repeat or something that it returns. So exactly whether repeat returns repeat or returns the result of calling repeat is something that you're going to have to work out on a kind of question by question basis. But what I'd say typically happens structurally, and we will read the question eventually. I'm just talking about looking at this example before I even know what it's asking and talking about it a little bit. What's going to happen eventually is that we're going to want to bundle, I think, some code with some data, with some variables. And to do that usually involves some kind of higher order function. Oh, and here we see one right here. So here's a case where we're creating a function g and returning it. And this function g would have f as something it could refer to. And that means that when you call g, you have I, what it's called on, and you have f, what you kind of cared about as its context, all bundled together in the name g. That's what happens when you have a function within a function. And that means that as you kind of call this thing over and over again, let's just pretend these are all g functions that we're calling, they can have slightly different behavior, same basic process, but maybe with some different data. Okay, so now we're going to have that in our mind. It's like we want to be able to return variants of the same thing over and over again, but sometimes change the data that's bundled with the function, and we have to achieve whatever it describes. So it says, implement repeat, which is a repeatable integer function that detects repeated arguments. As a side effect of repeated calls, it prints each argument that has been used before in a sequence of repeated calls. Therefore, if an argument appears n times, it is printed n minus 1 times in total, each time other than the first. The detector function is part of the implementation. You must determine how it is used. Oh, so we have to figure this out. And no lists or sets or anything else that we haven't covered in the course yet. Okay, so this looks like it's in scope for this midterm. So the kind of thing that you should be able to solve. That doesn't mean it's easy to solve, but if you work through it methodically, maybe we'll get there. The only place where you can do work, it seems, is here. So let's think about what that work might be. It seems like we're going to call a function on a number I. So I think probably 7 is going to be one of these i's, and 3, and stuff like that. And here's a case where it actually printed something, is that the second time we called it on 7, it printed this 7. So we need an if statement that says something like, well, if I've seen I before, then I want to print it out. This might not be my final answer, but I think we should just get started anyway. We're going to have to edit this later. I before. I don't know how to say that yet, but I'll try to figure it out soon. Then I want to print I. Good. I feel like I got some partial credit. And detector is gonna return G, which is the function that takes in 7. And now we think about what it takes in is a number. What it gives back is another function that does this kind of work. So here's an opportunity for self-reference. I think there's 2 reasonable candidates. You could either return G itself, some self-reference there, or I could return something that returns G. And in fact, detector returns G. Okay. So I think it's one of these 2, because these are both different ways of returning G. This return G would be return the G I've already created, which behaves identically to the one that I'm currently calling. Calling detector on something and having it return G actually would return a new G. It would return one that has a new F argument. It is the case that things need to change, right? Like the first time I called this on 7, it didn't print 7. Oh, what have I done? Well, whatever. I'll point with this. The first time I called on 7, it didn't print 7. The second time I called on 7, it did print 7. So just returning the same G that I was calling before would kind of just make it always do the same thing, which we don't want. We want a new function. So this one's out, this one's in, and now we have a way of returning G which has a different F. I'm going to pause here for questions, then we're going to figure out what F is, then we're going to fill in this line. Questions? Okay. Oh, there's chat. Oh, none so far. Okay. So how do I know if I've seen I so far? The only thing I can refer to is I itself, and whatever F is, and whatever repeat is. And repeat doesn't seem like it's the kind of thing that tells me whether I've seen I before. So that must be F's job. Now I need to build a new F. Well, in the beginning, I would say that I've never seen okay, so let's think about F. F is something that tells me whether I've seen I before. If I call it here, it's supposed to return true because I saw 7 earlier. How would I have built the F that did that? Here's my opportunity to construct an F that when I call G again on 7 the second time, I actually notice that I've done so. Well, what if F was a function that took in the new I from the next call and figured out whether new I from next call, oh, all right, I made it too long. Let's just call it new I. New I from the next call is equal to I. Let's imagine what will happen. The first time I call G on 7, it will find out, oh, I've never seen a 7 before, so it won't print it, but it will call detector with an F function that looks at whatever the next new I that comes in and sees whether it's equal to I. Now, which I is this? This is the 7 that I just called G on. So this will be a function that says, is the next thing that I see equal to 7? That got us through this call. And we return the result of calling detector, which returns G. And then I call that on 7 again. When I call that on 7 again, now I'm calling it with a new f, the f that says, is I 7? And it is, so we'll print it out. So the two important parts here are that this is what we just called G on, and this is what we haven't called G on yet, right? It's an argument of a lambda which hasn't been called. It won't be called. Instead, it will be stored as the name f until G is called again on the next 7, and then it will be called. We're not done, but we have detected 2 7s in a row and printed out the second one, which I think is good progress. I'm going to pause here, see if there's more questions. Okay, so there's a suggestion is like, what about older numbers and things that have been passed in this repeated call, not just previously, but before that? Couldn't you use an or to capture that sentiment? And yes, absolutely. But that's like slightly more complicated than the simpler version, which just looks at the last number and sees if it's the same as the current number. And once we can understand that, then we can handle all the past numbers too. So the numbers get passed into G and F. It's always a function that checks whether the next number is the same as the number currently. Yes, the version we have here says that F is always going to be a check to see if the current I is the same as the last I. So it'll detect 2 7s in a row. It won't detect the one that's repeated from this one that was long ago. Like the version we have on the screen right now only really detects 2 numbers in a row. We're going to try to extend it to handle the fact that 1 is supposed to get printed even if there was a 1 long ago. Just haven't done that. Okay, and there was a question of how does this track what's seen before? So here we got to just get conceptual. And we need to trace. So repeat is going to somehow give us a G, which is going to take in the number 7. It's going to see if we saw 7 before. If so, print it out. And then we're going to call detector, which returns on G, same G, but with a new F. Here's the F that tells you I just saw the number 7. So it returns true if anything else that comes in is equal to the current value of I. Here's where we're able to achieve some memory. It's bundled in the function f. Functions can encode anything. They can encode information, behavior, they're very general things. This f has the job of encoding what has been seen before. The way that it does it is to reference the I that was just passed in. So it's like part of this function, which we're passing in as the new f, that it knows what I was just passed in last time and is ready to look for new I's and see if they're the same. So this keeps track of what was just seen. Now, I guess the question is, how do you extend it so that it can track everything that's ever been seen? And here, we need to not just refer to the I that we just saw, but we need some notion of everything we saw before. And everything we saw before is F. Okay, what just happened? I said, next time, give me a G that, when it tries to figure out whether I've seen I before, it returns true if this new I that it comes in is equal to the current I that I just saw. Or if the new I that came in is equal to any I that was seen previously. And why does F encode everything that was seen previously? Well, that's because that's what we said it does. It's the one that tells you whether or not you've seen it before. Someone commented, this looks just like announce highest in the Hog project. Exactly. So if you understood announce highest in the Hog project, you could understand this too. It's a way of using a function to remember what happened before. And every time you want to do something again, you don't just want to do it with the F you had. You want to do it with the F that encodes some new piece of information as well. So in the Hog project, you were encoding the fact that there was a new high score that was the highest that had ever happened on a turn. In this one, you're encoding a new F, an F that tells you all the i's that have ever been passed into this G function. Okay, so a follow-up question is, wouldn't this F of new I still only check whether new I is the same as the current I? Well, we're kind of building things up. So we start with an F that just checks for 1. And then we build an F that checks for 7 or 1. And then we build an F that checks for 7 or 1. Then we build an F that checks for 3 or 7 or 1. Then we build an F that checks for 4 or 3 or 7 or 1. So in that sense, we're kind of accumulating information because this F calls the previous F, calls the previous F, calls the previous F. How do we write that down in code? Well, we just say the most recent F is the one that I want to call. But by passing this whole lambda in as an argument to detector, now we've built a new F. Where is this new F? Well, it's part of the environment for the function G, which is actually what we're returning here and call it. So is it the case that every time you call F, you're actually calling all the Fs that were ever created? Well, yes. I mean, until you actually find the I that you're looking for, every time you call an F, it's going to call the last F, which is going to call the F before that, which is going to call the F before that until one of them returns true. If one of them returns true, then you never do the second half of the OR because the first half returned true. Okay, so we made some progress. Let's finish this up. Now we have a mechanism for detecting, but how do we get it started? Well, repeat takes in a number. We know that 1 was never seen before, and we know we're going to call some function on k, which is the number 1. I think we should probably call g on k. So how do we get a g? Can we do it like this? The answer is no, because G is not defined in the global frame. It is an inner function for detector. The only way to get a G is to call detector. When you call detector, you have to call it on something that will work in this slot. And it will give you a G, which is good. But it will only give you a G if it actually, well, I guess it will always give you a G. So that's fine. But when you then call it on the number 1, it's going to execute the body of G, which is going to call whatever we pass in here on the number 1. Some function that I can call on 1. Why did I say call on 1? What's going to happen is I call repeat on 1. K is 1. So I call detector on some function, which gives me back G, which I then call on K, which is 1, which means I'm going to execute the body of G, which means I'm going to call F. But what's F? It's this function that I'm creating right here is going to be called on the number 1. And what's it supposed to do? It's supposed to tell me whether I've seen 1 before. Have I seen 1 before? No, I haven't seen anything before. No matter what comes in, I haven't seen it before. Now we're done. I think the key to solving these problems is to know this mechanism, which is that if you're like calling the same function over and over again, you got to figure out which function you're calling. It's G. How do I know it's G? Well, it does this thing, which decides whether or not to print. And there's only one place in this whole template where it's possible for me to say something like that. So it must be G that I'm calling all over and over and again. And if G is going to be something that does work and then returns a G, you have to figure out how to return G. And the answer is you find something that builds a new G for you. And now you have to have the work of figuring out how to like update the logic of G so that it does something slightly different each time. It's always checking to see whether I've seen the argument before, but the world has changed. The environment has changed each time I call G, and so I need a new G to do that. So kind of knowing that mechanism is really important. Beyond that, the key is like any other problem, which is to figure out what all these names mean and what they're going to do. So K is easy because you've got an example. It's just the first thing that comes in. I think is pretty easy too. Once you know you're just returning a bunch of G's, then you know these are the I's that are going to come in. So you know what I means. You know what G does. It sometimes prints and returns a new G. You know what K does. You know what repeat does. The only thing you don't know what it does is F. And there you have to ask yourself, what is the last piece I need in order to make this logic work? Well, the answer is I need to know whether I've seen I before. So that must be what F does. Now that's not an obvious thing. That's something you have to think about the implementation. But there's nowhere else to put this logic of like, have I seen I before? Than in F. So it must be there. So TLDR, figure out what the names are doing, what the variables are doing, what do they mean, and then you can implement your function. So we're in fall 2019, midterm 1, question 4a, and I don't think I've looked at this question in 2 years, so we'll try to rediscover it together. Two adjacent digits in a non-negative integer are an increase if the left digit is smaller than the right, and a decrease if the left digit is larger than the right. Okay. You can use the sign function below in all parts of this question, which tells you that if x is positive, we return 1, and x is negative, we return -1. So why might this be useful, by the way? We could take the difference between two adjacent digits, like 7 minus 2, would give me 5. And that could count as 1 if it's a positive number. So this could let me kind of count the number of positive and negative things that happen. We'll discover whether that's relevant or not in a minute. Implement ramp, which takes a non-negative integer n and returns whether it has more increases than decreases when reading its digits from left to right. So we have some initial conditions like n, where we start with an n, but here we have a different n. We have last. I'm guessing that's going to be the last digit that has been considered. And we have tally, which starts out at 0. So here's what I'm thinking, is I want to count how many times we've seen an increase, subtract how many times I've seen a decrease, and if I end up with a positive number, then there were more increases than decreases. To get that far, probably you'd have to think for a while. Like I just said it because I wrote this problem. But yeah, that kind of coming up with a strategy sometimes takes some time. So don't feel like you're supposed to instantly know what to do. But there's a clue here, which is, you know, tally is a word, at least for me, that invokes a notion of keeping track of things. And of course, we're going to have to keep track of something because we have to figure out whether it has more increases than decreases. So this notion that, you know, you'd add 1 every time there's an increase, you subtract 1 every time there's a decrease. And if you end up with more increases than decreases, then the total tally will be positive, is something that you just have to figure out. And I know it's not always easy to figure that out, but it's also not necessary that you solve every question on the exam in order to do well. So you just do your best to think through it and wonder, like, example by example, how would I do this? Compare 5 to 1. Oh, that's an increase. Compare 1 to 3. Oh, that's a decrease. Compare 3 to 1. Oh, that's an increase. So I should have gotten 1, and then I'm back to 0, and now I'm back to 1, and so I see that it has more increases than decreases. That's the idea. Now let's see if we can implement something. Tally is 0, n and last. Okay, so we said meaning, I feel like last might be the digit that is at the end. So that every time I shave off the last digit, it's kind of a common pattern. Now I'm gonna do, oh, I already screwed up. N. Okay. Now I'm gonna do the same thing, it looks like, but I'm gonna like update tally. To update tally means you have to have whatever was the tally before. And then I need some expression that is +1 for an increase and -1 for a decrease. It is not crazy at all to write out something like that while you're taking the exam to try to figure out what it is that you're trying to build. And then you can fill it in. How do I come up with such an expression? Well, I want something that's either 1 or -1, and I was told to use the sign function, and it returns 1 and -1. So that seems pretty good. What goes into the sign function? Well, it's a number where if it's positive, we get the 1. And if it's negative, we get the -1. If it's 0, then it doesn't count. So we need to be very careful about what we're comparing. It's an increase if 5 is bigger than 1, meaning the last digit is bigger than the next to last digit. Once I've done that, then I just need to figure out whether tally is bigger than 0. And I think I've implemented the logic that I talked about. Oh my gosh, you want to do for C now. What if that's harder? Okay. Read this first. The process function below uses tally and result functions to analyze all adjacent pairs of digits in a non-negative integer n. A tally function is called on each pair of adjacent digits. Process n using tally and this result, while n is greater than or equal to 10, I get a new tally from the old tally. So I get a new function from the old function. Sounds self-referential. And I also get some other value, the result, which is a function that I can call just as soon as n has gotten all the way down below 10, and that means there are no more pairs of digits. Okay, I will preface this by saying I think this looks like the kind of question that most people don't get. So if you can get other questions on the exam, you're doing well. But let's do it together. Implement ups, which returns two functions that can be passed as tally and result arguments to process, so that process computes whether a non-negative integer n has exactly k increases. We want to know whether there are k increases. Well, every time I see the last digit and the second to last digit, so this f must be a tally function, takes two numbers. I'm supposed to determine whether I'm supposed to somehow like count how many times they're the same. Oh no, increases. How many times right is bigger than left, so that in the end I can check and make sure that it's equal to k. Kind of keeping, and like what context do I have? Again, I have k. So if I want to see k things, and I always get k as context every time I return a new f, then basically I think I'll count now. So if k starts out at 5, and I see two digits where they're an increase, then I'll get a new f where k is 4. And then if I see two digits that are an increase, I'll get a new f where k is 3. And eventually, if I get a k that is 0, I'll know that I have seen exactly k increases for the original k. I'm moving a little faster this time, but it's the same logic as the one we did before, where you look at the function you're going to call over and over again. Tally, 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 tally. And you say, what information does it keep as context? It's just the number k. And so how am I going to see whether I did something exactly k times? Well, I'm just going to keep reducing k by 1 until it gets to 0, and then I'll know I did it k times. Okay. So it's the job of f, my tally function, to return a new f and a new result. So I think the only way I can do that is call ups. And ups takes a number. Which number am I going to pass in? Well, I think it depends on whether left and right are equal. Oh no, right is bigger than left. That's what we want. So I'm going to take right minus left. I want to know if that's a 1. Then I want to subtract that from k. Let's see how we're going to do that. Oh, you can use the sign from the previous place and the built-in max and min functions. You should look at the hint. That's what you should do. Okay, so we want something that's k or k minus 1. So that's the min of k. And how would we get k minus 1? Well, that would only happen if right was bigger than left. So this turned into positive 1. Okay, I think that'll do it. Why do I have a min here? Well, I don't ever want k to come up. And remember, if right is smaller than left, then sine of right minus left is going to give me -1. K minus -1 would give me k plus 1, which is not something I'm interested in. I only want k or k minus 1. This will give me either k or k minus 1. What do I know about this blank? Ups returns tally and result functions. Tally function takes 2 arguments and gives me back tally and result functions. Return a result function. What the heck is a result function? At the end of the day, the result function, when you call it, is supposed to tell you whether or not you saw exactly k increases. It's a function. How many arguments does it take? Well, we can look at what happens when you call it. You call it with no arguments, so it must take no arguments. And it tells me whether I've already seen exactly k increases. Every time I go through this and I see an increase, I subtract 1 from k. If k is all the way down to 0, then I've seen exactly k increases already. The question is, what happens if we define a function which returns print of x? You call f on 3. You see a 3. Isn't that the same thing as just returning x? Well, it's not, for the following reason. If I say y equals f of 3, there's a 3 there, and there's no y. In fact, f returned none. But right before it returned none, it printed out its argument. So it looked like it was returning 3 here, but it wasn't. And we saw that it wasn't when we tried to combine the result of calling f of 3 in some larger statement or expression. And so likewise, you can't call f of 3 in this case, because f isn't, I mean, you can, but it's not like keeping the 3 around, because f is not returning the 3, so you can't do anything with its result. Life's pretty different. If you return x instead of return print of x, now if you call g of 3, then this returns 3, which passes it into this, which returns 3, which passes it into this, which returns 3, and you see the 3. And you might wonder, how come this didn't like show you a none anywhere? And that's because it's a special rule of the interactive interpreter in Python. And this is a rule you're meant to know, that if you have a function, h, which returns none, and you call it, it doesn't show you the none. The only way to see a none is to print it out. Not true of a 3. A 3 you'll see automatically, whether you print it out or you don't. The rule is that Python will display the value of this expression that gets evaluated, whatever it is, unless it's none. So it doesn't automatically display none. It does automatically display any other value.